So let's make these planets in p5.js. So first we make a sphere shape here. Just be careful that I set some properties in the setup and the draw function like this. Now in the draw function I make a nested loop. Alright, inside that I draw a point with the vertex function. But for the xyz coordinates, I write 3 parametric equations of something called the spherical coordinate system. Alright, sphere shows... oops. I make this range to 360. Alright, a sphere shows up. If you are not familiar with the spherical coordinate system, that's another coordinate system alongside the Cartesian coordinate system. I don't explain the detail in this video, but if you go to the Wikipedia page, you can find the equations and explanations. In this code, we just plotted a lot of points during constantly changing the vertical and horizontal angles by the nested for loop, and that's why we are seeing this sphere. Alright, then we're gonna bring the Perlin Noise to create this planetary looking. But we need to be a bit creative here when we map the Perlin Noise on spherical shape. Let me explain what I mean by that. The chances are you have seen this cloudy texture or this procedural terrain using the Perlin Noise. Both are generated by the two-dimensional Perlin Noise. So this is the sample code of the Perlin Noise terrain, this. And at here in the noise function, there are 2 noise offset 1 and 2, right? And inside the first for loop, the offset 1 increases, and in the second loop, the offset 2 increases too. So eventually the noise values are different vertically and horizontally at each vertex, okay? But when we try to use the same logic on the spherical shape, there's a problem. Yeah, you might already realize that the first and last value don't match up. And that's true for the both vertically and horizontally, right? The 2 ends don't match up. So when we try the same method on the sphere shape, what happens? So first I declare 2 variables for offset, and I apply the noise value to the color, also apply on the radius. Then I increase the offset 2 inside the second for loop, also increase the offset 1 inside the first one. Lastly, reinitialize the offset 1 at here and offset 2 at here. Alright, let's refresh the page. Yep, this happens. We clearly see this artifact, right? The noise values at angle 0 and angle 360 are not matching up. So, how do we tackle this problem? Actually, the solution has provided over 3 years ago by this man, there, Daniel Schiffman. Maybe you watched, maybe not. In his coding challenge episode 136, he showed us this 2D Perlin noise loop. The start beautifully matches up with the end, right? To create that shape, he didn't use this one-dimensional noise. Because again, even though we map the values to the radius of the polar coordinate system, the both ends won't match up each other, right? So instead, he thought about this two-dimensional noise field. Then walked through circular path by polar coordinate system to take the Perlin noise values. For instance, this noise value is influenced to this value because they are so close. So this value to this one to this one, to the end. That's the same for every location in this field. So when we assign the circular path of the Perlin noise values to the radius of the circle, the last value matches up with the first one. Essentially what we're gonna do in this video is kinda 3D version of the Schiffman's work. So we think about this 3D noise field, then take noise values by walking this spherical path. Alright, let's work on that. First, I actually remove these offset increments. Then I make 3 variables named noise xyz and assign parametric equations of the spherical coordinate system to the variables. Okay, I give the noise function the 3 noise values as arguments. Alright, let's refresh the page. Yeah, now we don't see the annoying artifact anymore. But you notice the shape is weirdly symmetrical, right? And that's because the sine and the cosine function return the value between -1 to 1. So these noise values also range from -1 to 1. So I want to actually map to these values to some positive range. Like, let's say from 0 to 2. Alright, now it's completely smooth. Now I remove the noise value from the radius. Adjust the noise value to achieve the planetary looking. I make the density much higher and make the point a little bit bigger. That's incredible. It's time to animate the noise. That definitely looks awesome. So I make one offset again and add that to the noise X. Increase right after the nested loop, like this. That's awesome. Very satisfying to watch. And make sure there is no artifact on North Pole and South Pole. Alright. But that's too slow, so I have the fee range, like 180. Alright. If you up this upper limit to something like 6, then you realize that the whole scale of the noise just zoomed out. Or if you set only X and Z back to 2, yeah, that looks just be squashed vertically, but that's creating more interesting result. Because some planets like Jupiter or Neptune have this kind of pattern because of high-speed jet stream. So now it's the exciting part. Let's give the planet this beautiful surface and add this nice gradual shadow, the sun, and the stars. First, I actually remove these offset for now. Then at above, I create two variables, rows and columns, which define the resolution, and an array to store all the position and color of the vertices. Next, I actually copy this nested loop in the setup function. Yeah, but in the setup function, instead of this shape function, I actually store this xyz coordinates into a vector. Then what I do next is assign these position vector and the hue value, the color value, into the array we just created. I replace the upper range of the theta and phi to the rows and curves, and multiply 180 divided by the rows to all the theta in the trigonometries, like this, and also multiply the phi by 360 divided by curves. Alright, and lastly change the increment of the nested loop to 1. Oh, I also change it to no stroke. Let's refresh the page once and open the console. If there is no problem so far, when you output the 2D array here, yeah, this array, and you will see this two-dimensional structure here. And make sure all the position and the color values are here. Oh wait, actually that's 3D array because we assigned the small arrays inside the 2D array. Okay, I think it's alright. Let's work on this nested loop in the draw function. First, I change this to the length of the array. But here, access the hue value in the array by writing like this. And right after that, I make a plane for the surface of the planet. I make a constraint not to go beyond the range. Inside this constraint, I connect each four closest vertices to make a plane. Lastly, I need to change this increment to 1. Oh, this is nice. Yeah, but I need to work a bit more to connect the first and the last of the index in the array. I copy this part and paste here. Okay, this part is for filling the vertical gap. I make a plane by connecting the two vertices belong to the last index of the columns and other two belong to the index 0. And I copy again, paste here, and this is for the little hole at the top. I connect all the vertices in the last index of the rows. Awesome, it's working. Now, it's time to put the solar. But before that, I move this part into a function named planet. Then I use this ping image to resemble the solar. So I put the image inside the project directory, and in the code I make a variable solar, also a function preload. Inside the function preload, import the ping image and assign to the variable. Inside the setup function, I set the image mode to center. And lastly, I make another function for the solar. Place the ping image far away, and also make it extremely big. Alright, let's call the function inside the draw function. Okay, this is beautiful. Let's put a point light at below to generate the shadow effect. Let's rotate a bit. Yeah. So, what do you think? Let's add the stars millions light years away. So I make another array, star position. Then in the setup function, I make a for loop. Inside that, I store 1000 position vectors that randomized by spherical coordinates into the array. And let's also randomize the brightness to make them look more realistic. Then I make a function stars. Just draw points on the vector's position. So call the function in the draw function. Now I don't see anything. Oh, why I got the error? What did I? Oh, yeah, because I didn't put the for loop here. Alright, now I see the stars. That looks beautiful. So far, maybe you realized few problems around the rendering. First, at least in my environment, look at this. There are some noisy dots on the surface of the planets. Can you see that? And another problem is when you zoom out the universe, like this. Yeah, you see the p5.js doesn't even try to render the object far from the camera. And the thing is, there's a quick fix for that. There is this function perspective. This function accesses the camera object in p5.js. The first argument is for intensity of the perspective. Yeah, the second one is the aspect ratio of the camera. And the last two values are for the limit of the rendering. I mean the range limit. I set 1 and 10,000 for the minimum and the maximum range, and this must solve the two problems. Alright, now I don't see the noisy dots on the surface. And let's zoom out. Yeah, when I zoomed out, I still see everything. Yeah, every object in the canvas. Now, I show you some variations of the looking of the planet. So, for now, I rotate the universe a little bit to see the day side of the surface. So I use this rotate XYZ. That's good. And also I set the resolution a little bit higher, like 200 to 100. Alright. In the setup function, this time I apply Perlin Noise to the saturation value. I map the noise value to 5 to 55. So in the draw function, I assign the noise value for the saturation, and set some bluish color for the hue. Awesome. This planet must be in Ice Age for a long time. And oh, I just realized that we don't need this noise XYZ here in the function planet, because now we store the noise values in the setup function. Oh, maybe I set these values to 5 for now. Or if you want to make a terrestrial planet which has continents just like the Earth, maybe you want to try another way of using the Perlin noise. So instead of mapping the noise value directly to the hue value, I map to 0 to a small floating number like 1.75. And after that, I subtract the integer part of the noise value, then map the fractional part to the hue value, to 150 to 260 for now. I apply the fractional part for the hue and brightness at this time. So I change this fill function to apply that values. Alright, what happened then? This looks nice, but it still feels like a toy. I think there's a room for exploratory improvement. Let's set the range limit much larger, like 16, and I change the hue value to orangish color, but make the difference of the brightness very subtle. Then yeah, now we have the planet of Arrakis. Did you watch the movie Dune? That was great, I loved that movie. Lastly, if you are new to my channel, I have another series for you. Create this beautiful 3D flower using the spherical coordinate system. I think you will like it.